So I wanted to do a diagram, not a diagram, I want to do a video of how we can draw the shear force and the bending moment diagrams and how we can make it relatively simple. This is the approach I prefer to take. I think they show some other ways in the textbook, but I'm hoping that, you know, with what I do in class in this video as well, it'll help start to make it look a little easier, because at first it can be very overwhelming. So the two main things that we're going to be thinking about today in this video that are going to be useful to us are these relationships between the shear force diagram and the distributed load, and also between the bending moment diagram and the shear force. So what we see in this picture is that, you know, the distributed load is some function of x, like we call it w of x. And it turns out that the slope of the shear force when there is a distributed load is equal to what that function is. The thing that we want to remember that's kind of important is because there's a sign that goes along with this. And so in the situation, which is of course more typical, where the distributed load is pointing down, this is a negative quantity. And so that's important to remember. And so it becomes kind of easy with some of the other tools that we learned in class and in the reading about how to draw the shear force, that we can also use this rule when we want to draw it where we have a distributed load, just remembering that basically if it's a flat one, the height of that distributed load is the slope of the shear force. Now, once we have a picture of the shear force, a similar relationship is true where the shear force function is the slope of the bending moment diagram. And we can also use some of the things that we know about how the bending moment diagram will change. For instance, if there's a couple, as there is in this picture, there's a discontinuity. So I'm going to actually be able to draw the shear force and the bending moment diagram without cutting this beam or doing anything like that. The only thing that I do need to do is I do need to figure out what the support reactions are at either end. So this picture's a little bit involved, and so let's go over and make sure we know what's involved, the forces and so on. So there's a 15 kilonewton load. It is actually 2 meters from point A, so it's 2 meters from the left-hand side of the beam. In the middle of the beam, we are shown that there is a clockwise couple of 20 kilonewton meters. Then 1 meter offset from where that couple is, there's a 2 meter stretch where we have a distributed load, and I forgot to mention that that has a height of 10 kilonewtons per meter. And so that's the W. All right, so if I'm going to try to draw these, as I said, the first thing that I need to do is I do need to determine the forces of the support reactions. So point A was a pin, so it had a possibility of having an AY and an AX. Point B was just a sphere, so there's only a B in the Y direction. So in the Y direction, we had AY and B. We also had the 15 kilonewton load, and then we had the 2 meter stretch where we had a 10 kilonewton per meter distributed load. So the area of that would be 10 times 2, which is 20. So we find that AY plus B will be equal to 35. So if we do the moments about point A, and just to, I'm not going to draw another picture, but this distributed load is equivalent to 20 kilonewtons, and it would be at a distance from the center of 2 meters. it's going to be right in the middle of that rectangle. So it's 1 meter from the end of the rectangle. So we're going to use that fact when we're writing the moment, so I wanted to make sure that you could follow what I was doing when I got to that point. So the first force that we come to when we move from point A and go across the beam is the 15 kilonewton load, which is down. It would cause a clockwise rotation, and so it's a negative moment. It's 2 meters from point A, so it's 15 times 2. The next thing we have is the couple, which is a 20 kilonewton meter moment, and it is clockwise, so that as well is negative. Then we have the force due to the distributed load, which would be placed at the middle of that distributed load. It's 2 meters from the center, and so that's going to end up being 5 meters from point A. And then finally, we have the support reaction at point B. That's the only force that's pointing up, and so that's the only one that's going to cause a counterclockwise rotation, so it's the only positive moment. And so when we solve for the support reaction at B, we find that it's 25 kilonewtons, which means that AY is equal to 10 kilonewtons. So now we're going to use that information to try to draw. First, we're going to do the shear force diagram. Now, one of the things that we talked about in class is every time there's a point force, that will cause a discontinuity or a jump in the shear force diagram in the direction of that force. So we're starting off with a force at A in the vertical direction going up of 10 kilonewtons. So that causes a vertical jump on this diagram. We're going to start off here. This is 10 kilonewtons. And then what happens if we want to use this relationship as we go from this end and approach the 15 kilonewton force, we could say because there's no distributed load, we would put in a 0 here, which would mean the slope of the shear force is 0, which makes it a flat line. And that's going to continue until we get to the 15 kilonewton downward force, which happens at 2 meters. Now we have 15 kilonewtons pointing down, so now we have a jump in the negative direction of 15, and so this is going to bring us to -5. And then we're going to continue. Now, as we move past that, now we're going past the 5 kilonewton force, and we don't have any forces until we reach the distributed load. So we're going to go from 2 meters to 4 meters with a slope of 0. And so it's going to be at -5 until we get to 4 meters. When we get to 4 meters, that's right where the distributed load begins. And so the distributed load has a W of 10, but because it's pointing down, we would say that at that location, the slope of the shear force diagram is -10. And so we're going to continue from 4 to 6 with a slope of -10. And so that would tell us that for every meter that we go horizontally, we're going to drop down 10. So at 5, we go to -15, and at 6, we're at -25. So yeah, this isn't drawn to scale, but you know what? I'm doing my best. And so it doesn't even look like it's equal, but right here, it goes to -25 because the slope here is -10 because that's the value of W W is negative because it's pointing down. And finally, the last thing that we can do is we know that at point B, there was a support reaction of 25 kilonewtons. It's going to cause a jump in that direction. It has a magnitude of 25 kilonewtons, and it brings us right back to 0, which is basically what we expect. So notice how I drew that shear force diagram. It wasn't actually too bad. I was just using my rules to determine what the shear force diagram would look like. Now, because of the fact that the bending moment does depend on the shear force, which is usually either a straight horizontal line or it's a slanted line, the bending moment can be a little bit more difficult to draw. The other rule that I want you to keep in mind that we learned is if there is a couple at a location, that will cause a discontinuity in the bending moment diagram, but the discontinuity in this case will have the opposite sense of the couple. So when the shear force diagram, when we had an applied force, the discontinuity was in the direction of the force. For the bending moment diagram, the discontinuity is in the opposite direction of the moment. So, for instance, we have the 20 kilonewton meter couple in the middle of the beam. That will cause a discontinuity. That's a negative moment, but it'll cause a positive jump, okay? Now, when we draw this bending moment diagram, we're going to use the fact that the slope of the bending moment is equal to the shear force diagram. So we start off and we see that for the first 2 meters, and so I'm going to try to keep this even, so this is 2 and this is 4, so this is 2 and 4, and then this is 6, just to keep it moment. So the value of the shear force is 10 when we go from 0 to 2. That's going to be the slope of the bending moment. So it's going to go from 0 to 20. So this is 20, right? Slope of 10 because of that, and it's positive. Now, here the slope is -5. So we're going to go, the slope isn't as steep, so in 2 meters, we're only going to go down 10. Again, not the best, but we go down to 10 when we get to 4. Like when we go to 4 meters, it should be at 10 kilonewton meters. Now, we have this jump. Remember, because now we've gotten to the point, all right, oops, I made a mistake. And that's okay, because we make mistakes. What I forgot to mention, I went right from 2 to 4, but I forgot that at 3 meters is where our couple is located. So I have to deal with that. So I go from 2 to 3, I'm just going to go down 5. So this is going to keep me at 15. And so now, and so this is like 3. Again, not all to scale, but now we're going to have a vertical jump in the positive direction of 20. So I'm going to go from 15 to 35. And that jump, that discontinuity, is because of the couple that was located there. Now, we still have, we're still in this region where the shear force has a value of -5. So from 3 to 4, I'm going to go down 5 again. And so when I get to 4, this has a value of 30, okay? Then, this is where it gets tricky, because when we go from 4 to 6, We need to know what the expression is for the shear force because of the fact that we're going to have to integrate to find the function for the bending moment here, because it's not as simple as this being a constant value. And so while the derivative is going to be some straight line function, I need to figure out what this looks like in terms of what kind of shape of the curve will it be. So I know that in this region, the shear force has a slope of -10. So it is V equals -10x, but there's got to be some sort of constant, which is the y-intercept. And so if I trace this all the way back, I want to see where this crosses. And what I found is that it crosses the y-axis or the v-axis where it's equal to 25. So this is plus 25. And so the dx, is equal to v, which is equal to 25 minus 10x. And so the integral of dm is equal to the integral of this, 25 minus 10x dx. This is equal to m minus the m at this value at 4, which the m at 4 was 30. And then this is going to be 25x minus 5x squared. So m is going to be equal to 30 minus 25x wait. Yeah, it's 20 plus 25x, I'm sorry, minus 5x squared. I knew it was concave down and I was having a sign issue because I lost track of my signs. But what I knew is that this is actually going to be a concave down parabola is the shape, and that's minus 5x squared tells me that it's concave down. And I can also, if I do some substitutions, I know that, you know, where it starts off, but I know that when x equals 6, it's going to go down to 0, and so I can just roughly sketch it like this. And so that's going to give me the final piece of the bending moment diagram. So yeah, the bending moment diagrams are a little bit more difficult to draw, but they are based on your shear force diagrams. And so I'm hoping that this is somewhat helpful to help you draw these diagrams. But this is sort of an idea of how we can do it. Basically using these rules, the rules we learned about point forces and couples and how they affect the diagrams, putting it all together makes it relatively simple for us to sketch up the diagrams. Sometimes we have to do a little bit of integration.